Hi, welcome to this course on the SI unit of amount of substance. This is a physics models course. Please do subscribe and share with friends, and also welcome you to log in free at my website physicsmodels.in and the mobile app Physics Models. The SI unit of the amount of substance is mole. The symbol is MOL, and it's a fundamental quantity in the SI system. Now, the peculiar thing is that the mole is not exactly mass, it's not exactly volume, and yet it's a measure of how much matter we have. This is applicable for gases, solids, liquids, elements in the periodic table, complex compounds, organic compounds, everything. So let's understand it clearly and how it all started.
The concept of mole indirectly started as far back as the year 1811, when the brilliant scientist Amadeo Avogadro proposed his law, or the hypothesis, because he could not prove it at that time. He said that if we take different gases and keep them at the same temperature and pressure, and if we keep them at equal volumes, inside those volumes, the number of atoms and molecules will be the same. It was sheer brilliance on his part. In equation terms, it looked very simple, that the volume of the gas is equal to some constant into the number of atoms or molecules. But he had introduced the concept of atoms and molecules, which nobody had even heard at that time. Now, Avogadro's law was applicable to gases, and we are talking about amount of substance for solids and liquids. Let's see how that happened. Here is a visualization of Avogadro's law, which will make it easy to appreciate what he said. There are three cylinders, three different gases shown in different colors. The position of the piston is same in all the three cylinders. Therefore, the volume between the edge of the piston and the end of the cylinder is same. And Avogadro said that the number of atoms or molecules inside each of these cylinders must be the same. So we are moving towards the argument that the amount of substance is the number of atoms or molecules. You can see how the argument is gradually developing. Avogadro's law had a huge implication for atomic mass. And how did that happen? Now, we have those three cylinders, we have the same volume, we have the same number of molecules or atoms, because some elements are in terms of molecules and some elements exist in terms of atoms in their free state. But different gases have different densities. Density is mass per unit volume. That means that the mass per unit atom or the mass per unit molecule must be different if the densities are different. Therefore, the implication was that all substances, and we are still in gases, all gases must have atoms and molecules of different masses, which all add up to the density of that particular gas. There may be a doubt arising in our minds that if Avogadro could not count the number of atoms and molecules way back in the year 1811, when were they counted and were they able to be counted at all? The answer is yes. The great scientist Jean Perrin got the Nobel Prize in 1926 when he established through his experiments that substances do certainly consist of atoms and that the number of atoms can be counted. The details of his experiment are complex and we can't go into that in this video, but I have given you a link, and if you're interested you can kindly study that. After the discovery and proof of the number of atoms, scientists were able to agree by the year 1971, that's 50 years later, that every substance consists of atoms and molecules as basic building blocks, and that they can be actually counted. And they came to an agreement that the amount of substance can be defined in terms of mole, symbol MOL, that 1 mole of any substance on earth should be that amount which has got 6.02214179 into 10 to the power 23 numbers of elementary entities. For example, iron will have 6.02214179 into 10 to the power 23 atoms. The sugar that we have every day will have 6.022 into 10 to the power 23 molecules in it. That would be 1 mole of sugar, and so on and so forth. The beauty of this definition is that while Avogadro's law was applicable for gases, scientists were able to extend that logic to solids and liquids as well. Were able to extend that logic to every element and compound existing on Earth. And therefore, we come to understand the definition of the SI unit of 1 mole as it existed in 1971. And let's go forward and see what were the changes made to that over time. Understanding the SI definition a little better, we see that carbon-12 has been taken as a reference. Carbon-12 is the most widely available isotope of carbon as compared to its other isotopes. That's the reason it was taken as a reference. And by then, scientists were sure through their experiments that 0.012 kg of this isotope will exactly contain 6.02214076 into 10 to the power 23 elementary entities, that's atoms. And carbon-12 therefore became the reference for the SI unit. And 1 mole of any substance, anything, sugar, salt, iron, cobalt, would be that amount of substance which will have these many numbers of elementary entities. Again, entities could be atoms or molecules depending upon the substance. The problem that scientists pointed out was that SI unit for amount of substance is referring to another SI unit called kg, and that 1 kg also was not very accurately defined in those days. It was based on a master reference of a platinum iridium bar kept in Paris, and so this problem had to be solved. There was a lot of debate and argument about the SI unit for amount of substance. We must talk about that. The very words amount of substance was debated because the SI unit for length, SI unit for time and mass did not have a word like amount of length or amount of time. So why should we have this amount of substance in this SI unit? But then no better words could be found. We could not say SI unit for substance. So therefore, this word has stayed till today. The second word was elementary entities. There was a hot debate about that because some substances have atoms as elementary entities like carbon-12. Some substances like, let's say, sugar or common salt will have molecules as elementary entities. So that was finally agreed that that word also has to stay, and that will depend on substance to substance. Now coming to this 0.012 kg of carbon-12, where did that come from? So we are entering into the realm of gram atomic mass. So hydrogen's atomic mass was taken as 1, and relative to that, the mass of the atoms of every other element was computed. And for example, carbon-12 is 12 times as heavy as hydrogen atom. So its gram atomic mass got defined as 12.011 grams in terms of grams. So let's get deeper into this concept of gram atomic mass or gram molecular weight. Elementary entity for any substance is the basic building block of that substance as it is available freely in nature, not something which is artificially made by man. Therefore, elements which exist in nature with building blocks as atoms are iron, carbon, helium, and so on. Gases such as hydrogen, chlorine, oxygen exist in nature with their basic building block being molecules. We can't go smaller than that. There are no hydrogen atoms freely floating around, for example. There are no chlorine atoms, no oxygen atoms. And many other compounds exist as molecules in nature, like water, nitrogen oxide, carbon dioxide, and so on. So everybody agreed that yes, this sounds good, and elementary entities should be defined in terms of how they are available in nature. So when we talk about SI unit, 1 mole for any substance, we have to clearly mention what is its elementary entity as available freely in nature. And the official definition includes elementary entities as atoms or molecules or electrons and other particles or groups of particles, provided they are available freely in nature. Coming to atomic mass, as I mentioned, it's a relative mass. 1 mole of hydrogen atom, that means 6.022 etc. into 10 to the power 23 atoms of hydrogen, has a gram mass equal to 1.0079. This is the gram atomic mass of hydrogen. Now let's get into the difference in meaning between gram atomic mass, and the mass of 1 Dalton. The atomic mass was defined relative to the mass of hydrogen, as we saw. The earlier unit was AMU, that got changed to Unified Atomic Mass Unit by the IUPAC, International Union of Pure and Applied Chemistry. Later, the SI committee deleted all those definitions and they came up with a new definition as Dalton, spelled with a small d, the symbol being DA with a capital D. That's important to note. And the definition was that 1 Dalton is having a mass of 1/12 of the carbon 12 mass. So if carbon 12 atom has a mass of 12.011 dA, which is 12 times that of the mass of a hydrogen atom, then 1/12 of the mass of carbon 12 was defined as precisely 1 Dalton. Now 1 Dalton is not 1 gram. 1 Dalton is very small, and that's 1.66053904 into 10 to the power minus 24 grams. Now let's go further and understand it even better. In this slide, I have explained the concept of atomic mass versus molar mass. Mass and weight are same, and we don't differentiate. In many textbooks you might see atomic weight, molecular weight, so don't worry about that. Now the difference in concept is like this. The C12 atom, one atom, has an atomic mass of 12.011 Dalton. That does not mean the C12 atom weighs 12.011 grams, no. The 1 mole of C12 having 6.022 etc. into 10 to the power 23 atoms, that whole chunk will have a mass of 12.011 grams. Similarly, if we take a molecule of CO2, we have to simply add the atomic weight of 1C and the atomic weight of oxygen multiplied by 2, and we will get the molecular mass of the CO2 molecule as 44.009 Dalton. 1 mole of that CO2 will have a mass of 44.009 grams. This slide is interesting. We take an example of water. we calculate the molecular mass and then the molar mass. So we start with molecular mass. That's known to be 17.999 Daltons. You can calculate that by doing H2 plus O and atomic mass and adding all of them. In terms of grams, this Dalton has to be multiplied by 1.66053904 into 10 to the power minus 24, and we'll get the mass in grams per molecule. This is not the grams per mole. Then we take 1 mole of water, maybe in a spoon or cup, by taking the Avogadro number of basic entities, that's molecules. So if you take these grams per molecule and multiply that by the number of molecules, you will get grams. And you can see that we are getting back the grams exactly. So this is how the definition of 1 mole is used to arrive at a mass of 1 mole. The Avogadro number that you see here was changed later by scientists to a more accurate number, which we will see in later slides. The calculation method for arriving at the mass of 1 mole of water is explained in this slide, and you can go through it at your leisure. This slide, I have given you an example of a compound XO2, where X could be anything. This gives you a general approach to calculating the mass of 1 mole of a compound. In January 2018, the IUPAC came up with a new definition of the mole and they announced it. And if you look at the news announcement, you will notice that the Avogadro constant has changed slightly. The number 6.022140076 has come, and that's what I meant by saying the number changed from before to now. We now arrive at the D-Day, 20th of May 2019, when the SI committee officially announced the new and latest definition of the mole. And if you see this definition, it says that it contains, 1 mole contains 6.022140076 into 10 to the power 23 elementary entities. There is no mention of carbon 12, the mass of carbon 12 and all that. So this definition got rid of the anomaly of kg. It got rid of the anomaly that the amount of substance depends on another SI unit called kg. So scientists were happy with that. Some professors said that the new definition is great because we are counting entities than measuring the mass of a sample. Here is a lovely picture of a spherical interferometer. This was used to measure Avogadro constant very, very accurately using a sphere of silicon. These kinds of measurements enable the SI committee to zero in on the precise and latest Avogadro constant. Very famous scientists came forward and said that the new SI definition of the amount of substance is easy to understand and it has removed a lot of confusion that prevailed previously. Even so, many scientists were not happy and they argued that the SI unit of mole is still confusing and should be removed from the SI altogether. And they said that why should carbon 12 be considered as the reference for the molar mass, and they proposed some alternative ways of defining mole. All these were not accepted and we are still sticking to the official SI definition of amount of substance. Let us now apply the SI unit for amount of substance to a daily life substance. On the left you see sugar and on the right common salt. Start with the formula for sugar, C12H22O11. Sum up the atomic masses in Dalton for each of these elements. So 12 into mass of 1 carbon 12 atom, 22 into the mass of 1 hydrogen atom, 11 into the mass of 1 oxygen atom, and you will get the molecular mass of sugar in Dalton, 342.299 Dalton. Therefore, 1 mole of sugar will have a mass of 342.299 grams, and the amount of substance would be 6.02214076 into 10 to the power 23 molecules of sugar in that 1 mole. I hope this is clear. Similarly, for finding out the mass of 1 mole of common salt, you can do the calculation as shown in this slide. In this table, I have summarized a number of substances, and the 3 columns tell you the atomic or molecular mass in Dalton, the molar mass in grams per mole, and the last column being constant across all substances, that is the number of elementary entities in 1 mole of the substance. I hope this completely clarifies for you the SI unit for the amount of substance. Thanks for your attention. If you haven't already done so, please do subscribe to our channel and share with your friends. That will help us a lot. We have around 250 plus videos which will help you cover the whole of high school physics. Please log in free of cost at our website, and you can also download the mobile app Physics Models. I hope you will find a beautiful bridge to cross the wonderful river of physics. Have fun and have a great day.